All right, well, hello everyone, and welcome back. In this video, we continue our discussion about linked lists. In particular, we're going to look at how we search, insert, and delete nodes within a linked list. We're also going to do some more examples about how we would use a linked list class and how we can declare and define constructor, destructor, and other member functions for a linked list class. If you haven't already done so, please make sure that you have reviewed our previous video introducing linked lists so that you're familiar with the arrow operator and other key topics needed in this video. So let's go ahead and get started. Here's our goals for today's video. First, we will briefly review the topics from our previous video, including how to create linked lists and how to use the arrow operator to manipulate linked lists. Here we're just doing a brief review, so if you need more practice, make sure you check out our previous video. You'll remember in our previous video, we drew a lot of pictures. Drawing pictures is incredibly helpful in order to help visualize what's happening in our linked lists. So today we will continue to write more C++ code and draw more pictures to help understand how we insert, delete, search, and step through a linked list. I highly recommend that you follow along with our examples and draw pictures with me. Watch these videos with pen and paper in hand so that you can get practice visualizing and coding linked lists. Finally, we're going to learn how to declare and implement some linked list classes. And we'll see how we can write constructor and destructor functions, as well as other member functions. And we'll gain some additional practice in more examples, showing how we can write code and draw pictures to implement the linked list class. So let's briefly start out with some review. One of the most important tools that you'll need to remember for linked lists is using the arrow operator. Remember that the arrow operator combines the actions of the dereferencing operator, or asterisk, and our dot operator. So for example, if I write the code head arrow data equals 23, this is the same as writing asterisk head dot data equals 23. Basically what we're doing is we're saying, go where the head pointer points. That's the asterisk part. And then we use the dot operator part, which is we set the data value in our struct to, in this case, value 23. Similarly, head arrow next equals null. That would go to this next pointer where head is pointing in that list node struct. And we would make our next pointer point at the null memory address. Make sure you're really comfortable using the arrow operator, because this is one of the most important tools we use to construct our linked lists. Let's briefly review the process that we learned last time for building a linked list. Remember, you can see our previous video for a more detailed review. So our first step in creating a linked list is we first have to declare a struct or an object to represent the nodes of our linked list. So for our purposes, we had been declaring this list node struct containing some variable named data and a list node type pointer called next. You do not have to call your struct list node. You can call it whatever you want, but you want to make sure that your struct contains some variable to store data and some pointer of that struct type so that we can connect our nodes to each other. In our second step, we need to declare a pointer variable that points to the head of our linked list. So most of the time, we call that pointer head. And here we would write list node star head to declare a pointer head. Which we will use that pointer to point to the front of our linked list. In step 3, we need to use the new operator to make that head pointer to point at a new node. This will create the first node of our linked list. In this case, we can write the code head equals new list node. This will take our pointer head and make it point to a new list node struct which contains an uninitialized value for data and next. Of course, after step 3, data and next are uninitialized. So in step 4, we need to use the arrow operator to update the values and the pointers in each of these nodes. So in this case, if I want to update my data value in my first node, I can write, for example, head arrow data equals 1. And I could write, for example, head arrow next equals null. This would take my existing node where head points, and it would make my data value contain the value 1, and it would make my next pointer point at the null memory address. So the arrow operator is really important for initializing our data inside each node. Finally, after we have created our first node, we can repeat these steps using the new operator and our next pointer within our nodes in order to add additional nodes. For example, I could write head arrow next points to a new list node, and that would take my existing linked list, and that would actually add a second node where my next pointer had been pointing. So for example, in this case, I could write some code to add a second node to my list. Finally, for the purposes of this course, you want to make sure that the last node of your list points to null. So you can see the next pointer in my second node, we included code to make sure that that node is pointing at the null memory address. And that's important because it allows us to make sure that we know exactly where the end of our list is. We'll see later in today's class that we often can use loops to step through our linked list, starting at the head, or where head points, and ending once we find that our list is pointing at null. So the null pointer is really important to designate the end of our linked list. Last time we also talked about some good practices for linked lists. So please make sure you remember these good practices as we go through our examples today. First good practice is make sure you check for an empty list before manipulating it. If your list is empty and you try to manipulate it or do math, you're probably going to create some runtime errors. So often we use an if statement and we double check. Make sure that our head pointer isn't pointing at null already. Otherwise, our list is empty. Also, we should always keep one pointer pointing to the head or to the first node of our linked list. And this pointer is often used as the argument in our functions. We'll see in some of our examples later that the head pointer is basically what allows us to access our first node and all the remaining nodes in a given linked list. Also, be careful not to lose access to that first node. So if we overwrite our pointer which pointed to the head, we would lose our ability to access our linked list. So for example, if we had a linked list like this, and we made head point somewhere else, then all of these nodes would be abandoned. And we would lose the ability to access that memory. It might not seem like a very big deal if there's only 3 nodes, but you can imagine if you have a program that is going through many linked lists and working with many nodes, if you have a bunch of abandoned nodes in your program, this can be a serious problem. If you lose access to a node, and you're no longer able to access this memory through pointers, you create what's called a lost node. Lost nodes create what's called memory leaks, where we have this extra memory that's being allocated, but we can't access it to delete it. These memory leaks will basically just occupy memory and cause our system to crash if we run out of memory. So to avoid memory leaks, always keep some pointer pointing to the head or to the first node of our linked list, and make sure you maintain connection to all nodes of your linked list. Because remember, if you make a pointer point somewhere else, then you would lose access to the nodes in that list. So you have to make sure each node has a connection to the other nodes in the list so that you can still access that data. Let's try a quick practice question before we move on. In this example, we have 2 linked lists. Let's assume they are of list node type. So let's just assume both lists have list node type nodes. So remember, our list node struct basically contains some int value named data and some list node type pointer named next. So we have 2 linked lists, and we want to attach the lists together. So notice we have 10, 20, 30. That is our first linked list. Then we have 40, 50, 60. That's our second linked list. So to attach the lists together, notice what we need to do. We need to make head's third node point not at null, but we need to make head's third node's next pointer. We want that next pointer to point where other list head points. So if we can take this next pointer and make it point over at other list head's first node, that's where other list head points, then the 2 lists will be connected. We can actually accomplish this with a single line of code. Notice we need to use the arrow operator. This first node is where head points. Second node is where head arrow next points. Third node is where head arrow next points. So in this case, we want to go to our third node, so we'll go to head arrow next, and we want to modify the next pointer. So I'm going to take this next pointer and make it point our other list head points. That's all there is to it. If we make this pointer point over here, then our two lists will be connected. Let's try one more example. In this example, we have our linked list, and look what we're trying to do. We have 3 nodes, 10, 20, 30. They're all of list node type. And now we're running some more code. Let's see what this first line does. List node star node to add equals new list node. Well, that's going to declare a list node type pointer named node to add. And we're going to make that pointer point at a new list node struct. So here we're declaring a pointer called node to add. And we are making the pointer point to a new list node struct. And then notice what these next two lines do, lines 2 and 3. Int value to add equals 99. Well, that's declaring an int variable named value to add. And then, look what we're doing here. In our next two lines, node to add arrow next equals null, we're going to make our next pointer where node to add points, point at null. And we're going to set node to add arrow data to hold the value 99, matching that int variable value to add. So in this case, these 3 lines declared an int named value to add and set it to 99. And then we also initialized node to add. We initialized node to add's node to contain data equals 99 and next equals null. Okay, here comes an interesting part. Look what happens on this 5th line. List node star temp equals head. Notice what this code does. This declared a new list node type pointer named temp and made it point where head points. Well, why would we need this temp pointer? Well, look what we do next. We have this code head equals node to add. So we're taking our head pointer here and head is no longer going to point where temp points. Instead, head is now pointing where node to add points. Notice now head and node to add point at the same thing. Well, and then finally, look what happens here on line 7. Node to add arrow next. We no longer want to point at null. We now want to point at temp. So notice what happened here. These 2 lines of code inserted node to add's node at the front of head's linked list. So our final result will look something like this. So notice head and node to add are pointing to our first node that contained 99. And then notice now our next pointer is pointing at the node containing 10, where temp points. Temp allowed us to save the location where head was before. So the key takeaway here is notice the temp pointer saved the location of head. And this allowed us to remember the location of our original linked list so that we did not abandon those nodes. Notice if we had not used that temp pointer, the minute we moved head to point at node to add, these 10, 20, 30 nodes would have vanished. We would have lost access to them. So it's very important, especially when we're inserting things into our linked list, that we need to maintain some contact with all of our nodes using pointers. Here, this temp pointer allowed us to remember the location of nodes 10, 20, 30 so that we could still access them later on. All right, so feel free to reach out if you have any questions on these basic linked list operations. If you need additional practice, make sure you check out our previous video. We will now learn some more advanced linked list operations, including inserting, stepping through a linked list, searching for nodes, and deleting nodes in a linked list. For the purposes of this course, these are the linked list operations that I expect you to know for the purpose of assignments and our final exam. So we've already covered the first two. Last time we learned how to add nodes to the beginning and end. And we also just reviewed another example of adding nodes to the beginning just a moment ago. So now let's focus on these next operations: inserting, stepping through, searching, and deleting our nodes. So first, let's start with inserting nodes. Let's start with a general overview here, and then we will go through this process step by step. So you need to be very careful when inserting a node into a linked list. Take a look at this picture from one of our assignments for some additional guidance. Notice that there are two main steps for inserting nodes. The first thing we do after we create that node that we want to insert is we need to add some connection from our node to insert's next pointer to the location in the existing list. So we're attaching the node that we want to insert first to that location where we want our node to be attached. Then notice the second step. Then we add a connection. So instead of making this next pointer point to the node containing 30, we instead change the next pointer to point at our new node. Notice that the order of these steps matters. Notice what would happen if we tried the wrong approach. So notice if we wanted to instead insert our node in the wrong order. If I first took my pointer here and connected it to the 25, then these nodes would be lost. So it's very important that first, before we do anything with our second node's pointer, we would first attach our node that we want to insert to its insertion point. Then connect the rest of our list. The reason for this is because we do not want to abandon any of our nodes or lose access to our head pointer. So the key takeaway for inserting nodes is you need to maintain some connection to your head and to all nodes at all times. So if I were to take this next pointer and just attach it to node containing 25, I would abandon that node containing 30. This would create a lost node. So we don't want to do this. We want to make sure if we are inserting the node, we first attach our new node to its insertion point, then we connect this. So we always maintain some connection to all the nodes in our list, and that way we avoid creating memory leaks and lost nodes. So let's go through this insertion process in a bit more detail and practice writing the C++ code for each step. In this example, we have a couple different linked lists. We have these nodes containing 10, 20, and 30, and we want to insert them between the node 40 and 50 of other list heads list. So notice our final list contains 10, 20, 30 inserted between the 40 and 50 node. Let's look at how we would perform this insertion step by step. I highly recommend that you follow along on pencil and paper as we go through this example. So first step for inserting our nodes is to identify the location where we want to insert those new nodes. So in this case, we want to take all three of these nodes, 10, 20, and 30, and we want to insert them between the 40 and 50 node. And so we recognize that the point where we want to connect this node would be something like this. We want to take our node containing 40 and make it connect to our node containing 10. Then we want our node containing 30 to connect back to the node containing 50. All right, so if you remember from our discussion earlier, after we've identified the location where we want to insert the nodes, we need to connect a pointer from the node that we want to insert to the insertion point at the existing list. So we want to connect the next pointer from the node we want to insert to the insertion point on the existing list. So remember, here we want to connect the third node in heads list. So the third node's next pointer in heads list to the second node in other list heads list. So remember, to do that, we need to write some C++ code using the arrow operator. So in this case, we need to write the code head, arrow next, arrow next, arrow next, because that will update the next pointer where head, arrow next point. And we want to make that pointer point where other list head, arrow next points. So once again, we go find head's third node, so that's head, arrow next, arrow next, arrow next. We find that pointer and we make it point where other list head, arrow next points. Here's the result that we get. So once again, you can see now we have kind of this two-headed list where other list head still connects to its nodes like before. But now we also have heads list. And now the third node from heads list is pointing at that second node of other list heads list. Notice how drawing pictures really helps keep track of how these nodes are oriented and who's pointing at who. All right, but we're only halfway done with this insertion. Our next step is we now need to connect other list head's first node. We need to connect that first node over to head's first node. So how would we connect other list heads first nodes next? I want to connect other list heads first nodes next pointer to head's first node. Well, if we want to access other list head's next value, we write other list head, arrow next. That will access this next pointer. And where do we want next to point? We want it to point where head points. Notice now that next pointer will no longer be pointing at the second node in other list heads list. Now we will have the following. We have our node containing 40, but that node now points where head points at that node containing 10, 20, and then 30. And only then do we point back at the remaining nodes. Notice so now we have successfully inserted heads 3 nodes into other list heads list. Notice the one issue that remains is that we have to update our head pointer to still point at our very first node. So just to summarize, by writing that code, other list head, arrow next points to head, that allowed us to successfully complete the insertion Now we just need to update head. Because we want to make sure that our head pointer always points at the very first node. Well, how would we do that? What code should we write in order to make our head pointer point at our very first node? Well, what's the memory address of our very first node? Our very first node is where other list head points. So if our very first node is located where other list head points, where should we make head point if we want head to point at the very first node? In this case, we just need to write the code head equals other list head. That will make our head pointer point at the same location as other list head. Note that since other list head is a pointer, other list head stores the memory address of our first node, so writing head equals other list head makes the head pointer point at the same location. So finally, we have successfully completed that insertion. So we must first connect the last part of our new node to the connection point or the insertion point. Then we connect our existing list to our new node. And finally, we update our head pointer such that our head pointer is pointing to the very first node in our list. Let's try a code sense question then. We just discussed that in order to insert nodes into a linked list, we need to add a link from the new node to the existing list, and then add a link from the existing list back to the new node. Question is, what would happen if we reversed the steps like shown below? Take a moment and think about it. What would happen if we first connected our existing list to the new node and then tried to connect our new node back to the next node of the existing list? Does it matter the order we do these steps? If your code sense thought that something was wrong, your code sense would be correct. As we discussed, we definitely need to pay attention to the order of the inserting node steps. Look what would happen if we instead made our next pointer point to the new list. The nodes 50 and 60 would be abandoned. These nodes become orphaned because we just disconnected those nodes from the head or other list head pointer. So we would lose access to these nodes. And this pointer next would no longer be connecting our node 40 to our node 50. It would now be connecting back this node 40 to the node containing 10. Notice then if we tried to connect our node back to the existing list, there would be nothing left to connect to because we no longer know the memory address of those nodes. So you need to be really careful. The key takeaway here is when inserting nodes, you first connect the new node to the existing list, and then add a node or add that connection from the existing list to the new node. And remember, we want to be careful not to orphan any nodes or lose access to any of our nodes. When inserting, make sure you create some connection and maintain that connection to the head pointer and to all your nodes at all times. Otherwise, you might lose nodes and create memory leaks, which could cause some serious problems. Let's now talk about stepping through a linked list. You'll remember from our discussion of the arrow operator that the arrow operator allows us to combine the dereferencing operator and the dot operator to step through our linked list. So if next is the name of our pointer in our node, we can use arrow next to advance to the next item. For example, this node is accessed by using asterisk head, or just using head arrow data, or head arrow next. If I want to access my second node, I would have to write head arrow next arrow data, or head arrow next in order to access the data and the next where head arrow next is pointing. So for example, if we look in these cout statements, head arrow data would return the value 10 because the pointer head is pointing at the node, which is our first node, and the first node's data value contains 10. Similarly, head arrow next arrow data would go where head arrow next points and return 20 because head arrow next points to the second node contains the data value 20. Finally, if we keep going, we see that our third node can be accessed using head arrow next because head arrow next points at that third node. So head arrow next would return the null memory address because we're pointing at null. Notice what happens here though. If I say head arrow next arrow data, as if there was another node here, we would return a null pointer exception error and our program would crash. This is a runtime error. So it's important to remember that you can't try to access memory at memory address 0. If you try to read or write data at memory address 0, you're going to create a runtime error called the null pointer exception. And then this last example is interesting. Head equals head arrow next. That would make our head pointer point to the second node, or to the next item in our linked list. Let's do a quick practice question then. Suppose we have this linked list below, and my pointer is currently pointing at the second node of our linked list. We want to advance my pointer to point at the third node. So we want to make my pointer point at the third node instead of the second. So question here is, which of the following lines of code would correctly advance my pointer to point at the next node, or third node in the list? See if you can identify it. Take a moment and think about it. Okay, well, let's talk through. Notice we want my pointer to point at this location. This location, the third node, is located at my pointer arrow next, right? Because my pointer is currently pointing at the second node, so my pointer arrow next is pointing at the third node. All right, so if we want my pointer to point at the third node, and the third node is located at my pointer arrow next, the correct answer here would be my pointer equals my pointer arrow next. Because we want to take my pointer and make it hold the memory address of the third node. Notice choice A is not correct because that's simply going to return the memory address of my pointer arrow next. This is not going to update my pointer. If we want to update the memory address where my pointer points, we have to use the assignment operator to assign it the value of my pointer arrow next's memory address. So therefore, in order to step through a linked list, we can use that arrow next in order to step through node by node in a linked list. There's a few important things to remember. First, in a singly linked list, like the ones we've covered, you can only go in one direction in the linked list. Since there's just one pointer and it's only pointing at the next node, we can only go from head toward the null pointer. If you take more advanced programming courses, you may learn about things called doubly linked lists, where each node has 2 pointers. And in the case of a doubly linked list, since you have 2 pointers with each node, it's possible to move forward and backward within a linked list. So I'm not going to ask you about doubly linked lists on exams in this course, but you can see that you can build all kinds of data structures using nodes, and so if we wanted to be able to travel in both directions, we could consider using a doubly linked list. One other thing to note is some books, like our old textbook, sometimes call the linked list pointers link, but very commonly in this class, we use the name next as the name of our pointer in our singly linked list. You'll notice if you have multiple pointers in each node, you might need to give each pointer a separate name, like left and right or forward and back. But in this case, we just call our pointer next, since we just have one pointer in each node. Okay, let's now cover how to search in a linked list. So one of the best ways to learn how to search in a linked list is to draw pictures and walk through the process. Let's suppose we have a linked list like this one, where we have the same list node type structs with data and next. And suppose this linked list contains the values 1, 2, and 3. Suppose we want to search to see if this linked list contains the value 3. Here is some pseudocode explaining how we would actually perform that search. First step is to declare a pointer called current, or whatever name you prefer, and we want it to point at the same type of struct as our node. So in this case, we could write the code list node star cur, because we want to declare that list node type pointer. And notice that we initialize our current pointer to initially point at head. So in this case, we have declared that pointer cur, and we have initialized it to first point where head points. This makes our current pointer point at the very first node. Our next step is to check whether the node cur is pointing at contains the desired value. So to do that, we need to use an if statement. If cur arrow data double equals the value we're looking for. So we got to check using an if statement. Is current arrow data is 1 equal to 3? Is 1 the value I'm looking for? If current arrow data does contain the desired value, then I could return cur. Basically, I would return that pointer pointing to that desired node. I could also, if I chose, return a true or a false, or increment a counting variable. Else, if I do not find the desired value, then I move to the next node. So if I do not find the value I want, then I simply write current equals current arrow next. And I would advance to the next node. And then notice this last point. If we search all the way until we reach null, the desired value must not be present in the list. So most of the time, we can actually use a while loop in this case. And we can say, while current does not point to null. So we continue running this loop as long as current is not pointing to null. But if this loop finishes and we still have not found our value, then we could return a false, return a 0, or return something else. So notice how important it is to know how to use loops and our arrow operator in order to manipulate linked lists. So here, our first step again was to declare that pointer cur, make it point at our head initially. And then we go through, starting at our first node. Is current arrow data the value we want? If it is, we return the value of cur to give ourselves the position of that desired node. Otherwise, we advance current to current arrow next, we move to the next node, check our second value. Is that the value we want? If it's not, we advance to our third value. If 3 is a value we want, then we would return the memory address of cur. Otherwise, we keep going until current points to null, and if we still haven't found the desired value when current points to null, then that means the value must not be present in our linked list. Let's cover a few more hints about searching, in particular related to searching and inserting. So it turns out, sometimes we run into applications, such as in our homework assignments, where we need to search through a linked list and also insert something once you find the location where you want to insert. So in this case, I recommend that you declare a pointer called prev or previous and another pointer called cur or current. So you have one pointer named cur, which points to the current location, a second pointer called previous, which points to the previous location. And you'd see that if I know the insertion point and the previous node, it makes it very fast and easy to insert something into our linked list. Here's an example. So notice here, suppose I discovered that I wanted to insert a node between where my current and previous pointers were pointing. So I could write some code similar to this one. First, I declare my pointers cur and previous. I initially have current point to head, previous point to null. And basically what I do is, just like before, I search through my linked list until I find the value where I want to insert. Once I find the place where I want to insert, I exit my loop. Until I find the place where I want to insert, I make my previous pointer point where current points, and I make current point to current arrow next in order to advance the pointers to the next node if my insertion point is not found. Once I have found the insertion point, it's really easy to insert using this code. First, I take node to insert's next pointer and I attach it where current points. Then, I take my previous next pointer and I make it connect to node to insert's location. One thing to be careful here is be careful of edge cases. If we need to insert in the front, middle, or back of the list, we need to have different code. If we need to insert at the front or very end of the list, the code will be slightly different. So you'd need to write your program carefully in order to make sure you capture these edge cases. Let's try another CodeSense question before we move on. In this question, we have two loops. And you can see that both of them are using previous and cur pointers to search through a list. See if you can identify the true statement. Take a moment and review the code and these statements. Pause the video if you need, and then we'll discuss. Alright, so what did you think? Let's go through these statements one by one and see if we can identify the true statement. First one, loop A is less efficient since it requires more code. Well, that could be true potentially, but depending on what the code is, simply looking at the amount of code is not necessarily a clear metric of efficiency. Let's look at choice B. Loop B could create an infinite loop. Is that true? Notice what happens here. While current arrow data is not desired value. Notice, if the desired value is not in the list, this while loop will always be true. So choice B is also true because we could create an infinite loop, but it turns out that choice C also happens to be true, because if we allow our current pointer to advance all the way until it reaches the end of the list, or null, we know that current arrow data will return an error. It will return that runtime exception error, or null pointer exception error, if current points to null. So in this case, what will happen is that, yes, we'll create an infinite loop, but once we reach the end of our list, we're going to get a runtime error. So eventually, we'll have that runtime error, assuming that our list has a null pointer at the very last node. So choice C is the best answer. Loop B could cause a runtime exception if the desired value is not present. So therefore, choice D must definitely be false. These loops are not equivalent because they would produce a different result. Notice our loop in our code A would actually stop once we found the null pointer and the end of our list. Alright, so let's now cover a few more important topics related to linked lists. If you take more advanced programming courses, you will see that linked lists are often used with classes to create more advanced data structures. So here we will introduce how to use linked lists with classes, constructors, and destructors in order to build some basic data structures. We'll also go through a couple more examples to help everybody practice the arrow operator and the tools we've learned. First item for today is constructors. You'll remember when we covered classes that you can create constructors as member functions to help initialize our objects. In this example, if I want to create an int linked list class and have a default constructor for that class, then I can actually declare this default constructor to initialize an int linked list object. So in this case, you'll notice we initialize our list to have length 0 and head pointing to null. It's a very good practice in constructors to initialize our pointers to null initially and initialize any data to a known value so that you know that your data is initially empty. For example, if we wanted to actually define this default constructor in our intLinkList.cpp file, you would see that all we would need to do in this default constructor is make our private variable head point to null, and we would initialize our length to be 0, because that was the desired initial conditions specified in the precondition and postcondition comments. So if you're ever writing constructors for a linked list or linked list class, make sure you pay attention to how you initialize your private variables. Generally, we want to make our head point to null to indicate an empty list, and if we have a length variable to track our length, we generally want that to be set to 0 initially. So earlier we learned about the delete operator and how, when working with dynamic memory, we have to delete the dynamic memory ourselves in order to save memory and clean up after ourselves. So whenever we work with dynamic memory, it's a good idea to also declare functions called destructors. Destructors are member functions that are used when we want to delete objects from a class. So destructors are really important when our class relies on dynamic memory. And you can see For this int linked list class, the convention is that you put a tilde in front of the class name in order to create a destructor. Here's a little more about destructors. Destructors are really important because they allow us to delete our linked lists and delete our nodes when we're finished using them. Remember, if we don't clean up after ourselves, if we don't delete our dynamic memory, we could run out of memory and cause our computer to crash. So when working with linked lists and objects that contain dynamic memory, it's a good idea to always include a destructor so that you can clean up your memory when you're finished using it. So it's very important. You'll often see this in our examples and assignments. If we have an object and a class that uses dynamic memory, it's a good idea to declare that destructor. So the destructor is actually one of my favorite functions that we cover in this course because it's actually really interesting how to declare and define a destructor in order to delete the nodes of a linked list. One way that you can define a destructor function is to use a loop to delete each node one by one from a linked list. Here's an example. This is one of my favorite functions that we use in this class. Suppose we wanted to delete this linked list. So if we were to call that destructor function on this linked list, notice what it does. We take our linked list and we look and we see, okay, as long as my head is not pointing to null, I'm going to run the following loop. I declare a pointer called oldHead, which points where head points. Then I take my head pointer, and I'm going to move it, so I make head point at head arrow next. So now my head pointer is pointing at the second node. Then I use the delete operator to delete oldHead. And now my loop will repeat, and notice now I have a linked list containing only 2 nodes. Once again, I make oldHead point where head points. I move my head pointer so that my head pointer now points at the second node. And I delete the oldHead. And we keep running this process as long as head doesn't point to null. So we still run a third time. So we make oldHead point where head points. Then we move head to our next, to where head arrow next points. We delete oldHead, and our final result will be our loop will stop because head is now pointing at null. And now we have deleted our entire linked list, and we have ended up with an empty list. So the purpose of the destructor is to delete these nodes and delete the dynamic memory and give us back our head pointer pointing to an empty list. This is really important in order to free up memory when we're done using it. So if we follow that approach for the destructor of the int linked list class, we would write the code for the destructor in a very similar way. Notice we would declare that oldHead pointer, and we would use the exact approach that we just illustrated to delete the nodes one at a time until head points to null. Here's a couple more things to note about destructors. You need to remember that destructors must be declared and defined by the programmer in order to actually delete stuff. So you have to declare and define your own destructors. The compiler is not going to do it for you. So just like with the default constructor, the compiler will create a destructor for you if you forget, but it'll be empty. We have to write the definition for the destructor in order to successfully delete our unwanted nodes. One more important point that is good to remember is the copy constructor. So when using linked lists and functions, if you pass a linked list into a function, we use pass by value. And this can be a problem when we're passing in pointers because pointers point to memory addresses. So when we pass a pointer by value, this is sometimes called creating a shallow copy. For example, if I have a function that uses a linked list like this, and I call my function on head, if I plug in that head pointer into my function, what I'm essentially doing is I'm plugging in a copy. So essentially, I have this copy of head that's pointing at the same memory. So here, a copy of head is plugged in. The problem with this is if I try to change some of the values in this linked list, I'm actually modifying the original linked list that I had rather than my own separate linked list. The copy constructor will take a linked list, such as the one that we are looking at here with head, and will make a copy. So in this case, the copy constructor is used to make what's called a deep copy at a unique memory address. So rather than just copying the head pointer's memory address, we create a copy of the entire linked list at a unique memory address. So a unique, separate memory address. So this is really important for data protection. It prevents our copy and our original linked list from sharing data at the same address, so it can help protect from errors and other problems. So this copy of the linked list at its own unique separate address, that's called a deep copy. I'm not going to ask you about this information on exams in this course, but you'll definitely want to know about shallow and deep copy if you take more advanced programming courses such as data structures class. All right, before we end, let's go ahead and try a couple quick practices. It's very good practice to try writing some functions in order to manipulate classes which contain linked lists. So in this case, we have that int_linked_list class that we were discussing earlier. And in this class, you'll see that each object of int_linked_list type contains a pointer called head and an int variable length. And we use the node struct in order to create additional nodes. So here we're being asked to write the add function to add a node containing element to the front of the list. So suppose we had an existing int linked list object that contained 3 nodes. If I called the function add with argument 9, then the result would be inserting a node containing 9 to the front of my list. So in this case, the strategy to add an element to the front of our list is that first we need to create a new node containing the desired value, or containing element, the value in the argument. Then we need to insert the node at the beginning of the list. And third step is we need to update the head pointer to make sure that head always points to the very first node. So let's go ahead and try updating this empty definition in order to correctly perform the add function. First, we need to create that new node containing the element from the argument. Here our nodes are made out of the node struct. So remember, it's not list node type anymore. We need to declare a node type pointer. So I'm just going to call it node star node to insert. And I'm going to make that new pointer point to a new node struct. So now I have just created that node to insert pointer that points to a new node. Next, I need to make node to insert contain the data value equal to element. So I can write node to insert arrow data equals element. And initially, I'm just going to go ahead and initialize node to insert's next pointer to point at null. So we've just created that first node. Now, we need to insert the new node at the beginning of the list. So remember, the new node is being pointed at by node to insert. And so in this case, all we need to do is we need to update the new node and make it in the front of our list. So here we just write node to insert, and we make its next pointer point at head of our existing list. So now, if I had this new node containing number 9, for example, notice I could just essentially perform this connection to make that node attach at the front where head points, and then we would get our desired result. But remember, we need to update the head pointer so that it points at the very first node. because initially head will actually be pointing at the second node once we've inserted the node to insert. So in this case, we need to take head and make it point at the node that is now located in front. So this will allow head to now point where node to insert had pointed. In this case, there's one last thing we need to do. I call it bookkeeping. We have this private variable length. Since we added a new node, we need to do bookkeeping. We need to update length to reflect that we added a new node. So in this case, we just write the code length plus plus to update our length and capture that we had successfully added an additional node to our list. Notice how drawing pictures and visualizing this process makes it a lot easier to write these functions. So if you see questions like this on a future assignment or on an exam, make sure you draw pictures to really visualize what's going on. It'll help a lot. Once again, here's an example of how that finished code would look. Let's try one more practice. Suppose we now want to write the function contains. Contains is a Bool type function, and it will return true if the element we want is inside our linked list. So for example, if we had that list from before, suppose we had something like this. If we ran the function contains and we said contains, for example, 5, that would be false because our current list does not contain the value 5. But if we said contains 2, then it would be true because 2 is present in our second node. So let's discuss our strategy here. In this case, we need to search through a linked list. So the strategy will first be to declare that current pointer. And we want to make that pointer cur point to the head initially. And then we check. We search until cur points to null or until the value is found. And basically, we just use that same if statement as before. We return true if the value is found, and if not found, advance to the next node. So we basically start with cur pointing at our first node. We check if our first node contains what we want. If it does, we return true. If it doesn't, we move cur to the next node. We check this node. Does that value contain what we want? If it does, we return true. If not, we move to the next node. And we keep repeating until we've either found the value we want or until we've reached null. If our loop ends and we still have not found the value we want, then we return false. So let's briefly write the code that we need to complete this contains function. As we noted, the first thing to do is to declare our cur pointer. And we want to make that current pointer point at head, or at the beginning of our linked list. Then we use our while loop to search through the linked list. So as long as our current pointer doesn't point to null, then we keep searching. First, we check whether the value cur points at the thing we want. So if current arrow data is equal to that desired value element. If current arrow data, if the value stored where cur points, if the value stored is what we want, then we're done. We return true and we carry on. If not, we don't even need the else statement here. We could just have the code. But basically, if this if statement does not trigger, then we need to advance cur to the next node. So if we don't find what we want, we move to the next node, we repeat our loop, and try again. If this loop finishes and we still have not found what we want, then our value must not be present, so we return false. So here's an example of what the contains function would look like when completed. You'd see that we use that exact while loop and the cur pointer to search through our list one element at a time until we either find the value we want or we return false. Finally, let's look at one last example. The remove function is really interesting because depending on what we're trying to remove, we need to account for some edge cases. If you look back at our int linked list declaration, the remove function is supposed to remove whatever node in our list contains element. So we'll get some argument in our linked list. For example, if we have that list from before, if we have the list containing 1, 2, 3, and we call remove on 2, then we would end up removing the node containing 2, and we'd be left with just 2 nodes in our list, remove 2, and node containing 1 would be connected to our node containing 3. So notice that depending on what argument is present in the remove function, we could potentially have multiple cases. If the list is empty, we want to do nothing. So if head points to null, we just return because there's nothing to remove. We don't want to create a runtime error, so we always want to check immediately to make sure our list is not empty. If the node that we want to remove is in the middle or the end of the list, then we can use our usual procedure that we learned in order to remove the node. So notice what we do is we declare current and previous pointers and a flag variable to check whether we found the value we're looking for. If we find the value we want to remove, we make our flag variable true and we exit our loop. If we do not find the element we're trying to remove, we advance our pointers and check the next node until we reach null or find the value. Notice here we have code to capture the case where if the item cannot be found. If element is not contained in the list, then we exit the remove function. Then we have a couple extra cases. If the node we want to remove is in the very beginning of the list, then we need to update our head pointer and then delete the node. Otherwise, if the node we want to remove is in the middle, then we make our previous pointer point where current points, and we delete. We make previous pointer point at the node after current, and then we delete where current points. Finally, notice that if we deleted a node, we need to make sure that we also decrease our length value to reflect that we had successfully deleted a node from our list. So definitely try going back through these examples yourself and try coding them up and playing with them. It's really good practice. Real quick, let's go ahead and demonstrate this int linked list class in C-Line. So we have our class declaration in int linked list.h, and we have our function definitions in the int linked list.cpp. So if we go ahead and run this program, you'll see that we have a main function that will actually go through and add elements to our linked list. We can check our contain function and verify that yes, indeed, we contain the value 10. And we also go through and we can remove everything. So our main function in int linked list main, it just goes through and tests out our different functions. Here we've declared some int linked list object named list. And notice what we did here. We used the add function to add 10 items to our list. And then we output, using this at function, we are able to output the location in the list for each element. So here, this first for loop added 10 items to our list, and then we outputted the value. We also tested our contains function, and we saw that our list does include the number 10. Notice if I changed my contain function to be 11, for example, and I ran it again, we would see that our list does not contain. In this case, I need to update the code here, but notice we trigger the fact that our list does not contain the value 11. And finally, we can go through and try removing all of our elements in our list. And we use our remove function to go through, remove everything. And now we can finally use our size function to return the size. And we see our list is now empty. So it's really great practice to go through this example and verify that you can reproduce all of these add and remove functions. I highly recommend that you try drawing pictures and coding this up to verify that you understand these topics. Let's go ahead and wrap up here for today. You should now be much more comfortable understanding how to create and manipulate linked lists in C++. Make sure you take the time you need to go back through and understand the arrow operator, how to write the constructor, destructor, add and remove functions, and how to manipulate a linked list by adding and removing nodes and inserting things at the beginning, end, or middle of the list, and how to step through a linked list. These are all really important topics that you'll use a lot in our last assignments and also in future programming courses you might take. So feel free to reach out if you have any questions, and we'll see you all in the next video.